Okay, today actually we introduce a new topic, that is another transform, that is Z transform. Okay, so till now we have seen the discrete time Fourier transform, discrete Fourier transform, okay, FFT also we have seen. Now this is the Z transform. Okay, so this is Z transform. It is in actually in
Sorry,
continuous time.
Rajini.
Okay.
Hello. Sorry,
Hello.
Rajini. I'm not so sure whether it is only me or the others, but I cannot see your PowerPoint.
Oh, it is not visible. Just a second. No?
Yeah, yeah, yeah. It's not visible. Yeah.
Okay. Now, can you see it?
Yes. Now it's better. Yeah. Yeah. Now I can see your slide.
Okay, okay, okay.
All right.
Okay. So, today we will start with this Z transform. In the continuous time domain, we have the Fourier transform, for which the variable is actually was the j omega. So previously we have done the Fourier transform. So the variable there was j omega. Now, for some signals, the Fourier transform does not exist. So, for such signal, we introduce a convergence factor. And so, let us say the convergence factor is, so previously in Fourier transform, we are having j omega t or n, suppose j omega n. Okay. Now, we introduce here a convergence factor e to the power minus sigma del, let us say delta t. Okay. Now the resultant signal, I would say, suppose we are applying this to some x of t. Okay, so the resultant signal is x of t into e to the power minus delta t here. Okay, now for this case, maybe if we choose proper delta value here, the Fourier transform may exist for the appropriate value of this delta. Okay. Now this precisely give rise to the Laplace transform. Now that Laplace transform, if we see, the Laplace transform is in terms of the complex value S. So we all know the Laplace transform S is equal to the sigma plus j omega here. Okay. Okay. So this represent the point in the complex plane. Okay. So one axis is the sigma axis, another axis, x axis, sigma axis, y axis, the j omega axis, like this. Okay. So Fourier transform is here, and I can say so here the Laplace transform is exist in this S plane. So we call that a S plane. This is basically the S plane, sigma and j omega. Okay. Now, basically, we are covering the complete S plane here in the Laplace transform. Now, the Z transform, if we think, so Z transform has the same kind of interpretation. Okay, so there are a sequence, maybe x of n is the sequence for which the Fourier transform does not exist, but the Z transform does exist. Okay, so in the Z transform, basically, we are having the Z plane over there. Okay, This is omega t. Now, in the Z transform, the convergence factor we say r to the power minus n. Okay, so we can choose r factor. This is, we can choose this. Okay, r can be anything. Okay, or otherwise I will say we can, this r has to be properly chosen so that the x of n, r of minus n has her Fourier transform. So this is the convergence factor here. Okay, r to the power minus n. Okay, so in the Fourier transform, the factor e to the power minus j omega n, and I'm having x of n it r to the power minus n. Okay, this is the convergent factor. So this I can say x of n r e to the power j omega, and this is minus n to the power minus n. This I can write, this term I can write like this. Okay, basically in Fourier transform, this variable r is equal to 1. R equal to 1 in the Fourier transform. Okay, so for Fourier transform, this r, for r equal to 1, we compute on the unit circle of the complex plane. Okay, and there the omega term, this omega term is a variable term. Okay, now in the Z transform, basically here, this is a Z plane. Okay, so this is the real Z, the x axis is the real Z. This J times the imaginary axis, that is the imaginary Z, I can say. Okay, and this I will say, this is having radius small r, and it is moving with respect to the speed omega, j omega. Okay, in the, please understand, in the Fourier transform, this r is restricted to the value 1. Okay, so in the Z transform, r can take any value. Okay, therefore we introduce the symbol Z here, and this Z is equal to r e to the power j omega. So Z we call, this is equal to r e to the power j omega. Okay, and if we do summation over there, then we say this is x of z. So x of z is x of n e to the power r e to the power j omega. Okay, so this the formal definition, we can say the formal definition of this x of z is, x of z is summation from minus infinity to plus infinity x of n z to the power minus n. Okay, otherwise you can say instead of z, this is summation from n equal to minus infinity to plus infinity x of n r e to the power j omega to the power minus n. Okay, so this is the formal definition of the Z transform, x of z. Okay, now this is basically exactly similar to the Laplace transform. You might have done this Laplace transform in your mathematics course. Okay, so this is similar to the Laplace transform in continuous time domain. Okay, but the properties are quite different. Okay, so z is a continuous complex variable and it has a magnitude r and angle omega. Okay, so this is a complex variable with magnitude r and the angle omega. Okay, now so this is the forward transformation, just now, just like we have done in the discrete Fourier transform. There is a forward transformation and the reverse transformation, inverse transformation. So like that we are also having a z transform, which is defined like this. Okay, now this is h of z, therefore here h of n, z to the power minus n. This is summation from n equal to minus infinity to plus infinity. Okay. So similarly, we are having the inverse z transform. This is called as the inverse z transform. This is the z transform. So inverse z transform is defined like this. So we can get back the variable h of n from h of z. Please understand this is h of z. So this is equal to 1 by 2 pi j integral over h of z, z n minus 1 dz. Okay, so today's lecture is basically focused only on the z transform. Okay, so in the next lecture we will see the inverse z transform. So today we will focus only on the z transform. Now in the z transform, basically there is a question of existence comes in the z transform. Does x of z exist or not? This is very important here. Does this x of z exist or not? Okay, now there is one sufficient condition, and that would be the new sequence x of n. Now this is a new sequence for us. X of n r of minus n is absolutely summable or square summable. Okay, there is one sufficient condition for the existence, that you need to check this new sequence x of n r of minus n is absolutely summable or square summable. These two things we need to check. Both absolute summability and the square summability are the sufficient conditions for this. Okay, they are not necessary, they are sufficient. Sufficient conditions are what? Absolute summable and the square summability. Okay, now we need to check for this sufficient conditions for the existence of this x of z. Okay, they are not necessary, they are sufficient. This also complicates matter because in Fourier transform we are only concerned with the circle of radius 1. Now this idea we are expanding it to the total z plane. Okay, z plane. Now therefore the question of this existence of x of z is in terms of ROC. So this ROC is nothing but the region of convergence. Okay. Now if the summation of this x of n r of minus z of minus n, this is not r of minus n, this is z of minus n, does not converge anywhere in the z plane, then we say that the z transform does not exist. Okay, so the existence of this z, the z transform We can also check with the region of convergence. Okay. If this x of n, z of minus n is not converging anywhere in the z plane, then we will say that x of this h of z is not exist. Okay. Now, in the Fourier transform, we were focused on the unit circle. Okay. Now, if the region of convergence of this Z transform includes this unit circle, this R equal to 1, then the Fourier transform will also exist. Okay. If the region of convergence, this is very important statement. So what we are talking about, we are talking about Z transform and the Fourier transform. Okay. Now, if the region of convergence, that is this ROC, if the ROC is included in the ROC, if unit circle is included, then the Fourier transform is also exist. Okay. Okay. But the vice versa is not true. Okay. So this you please remember, because the Fourier transform may exist, but the Z transform may not exist. Okay, here Z transform is also existed and Fourier transform is also existed. Why? Because in the region of convergence, this unit circle is included. Okay, so this is very important statement regarding the Fourier transform. Okay, now the region of Z plane where the magnitude of this h of z is not infinity. So the magnitude of this h of z is less than equal to this alpha value, which is not equal to the infinity. Okay, so the converge means this h of z has a true value, which is not infinity. So that is the convergence. Okay, so this is very important, the convergence of this. Now let us take one example on this to understand more. Okay, so before going towards this first example, let us check Z transform of the delta function. Okay, let us say I'm having x of n equal to delta of n. Okay, so if I want to find the Z transform of this, so I will do summation over n delta of n z of minus n. But this delta of n is only exist for n equal to 0. Okay, therefore, this x of z is basically equal to 1. Okay. So we can say that the z transform of this delta of n exists at all values of z. This is exist for all values of z. Okay, so this will be from r equal to 0 to r equal to infinity, this entire z plane. Okay, so ROC for this delta of n is basically entire z plane. Okay, total z plane. So when we calculate the z transform for any sequence, So basically, we also need to define the region of convergence for that. Okay. So for this first example, delta of n, so we know that x of z is equal to 1 because it only exists for n equal to 0. Then the region of convergence, we say that this cover entire z plane. Okay. Now let us take another example, like this example. Okay. Now I am having the function h of n is equal to alpha to the power n u of n. Okay. Now apply z transform for this. So h of z is defined like this: n summation over n equal to minus infinity to plus infinity. This is the given h of n, that is 8 alpha to the power n u of n, and then z of minus n. Okay. Now this u of n is basically a step function which only exists from n equal to 0 to infinity, in the positive half only. Therefore, this summation is only from n equal to 0 to infinity, alpha to the power n, okay, and z of minus n. Correct. Now, z of minus n, we keep n separate. Then this is alpha z to the power minus 1. Okay. Now, for this summation, we can apply the standard formula to calculate this summation. So this summation can be calculated for this. This is the formula for that. So summation of a to the power n is summation over this small n is equal to n capital N to m. So if we are doing summation of this a of n over this n to m, this is basically equal to a to the power small capital N minus, which is the lower limit of the summation, minus a to the power m plus 1 divide by 1 minus a. Okay. If the same formula, if we apply for alpha to the power alpha z of minus 1, so what we are doing summation from n equal to 0 to infinity alpha z to the power minus 1 to the power n. Okay. So this term we can write like this. Okay. So this we can write like this. So this is basically capital A to the power, the lower limit is 0 minus the upper limit plus 1 divide by 1 minus the term A. Okay. Now this is our Z transform of this alpha to the power n z of minus 1. Now this h of z should not be equal to minus infinity. We have seen here. Okay. The convergence is very important here for existence of z transform. So this term, denominator term 1 minus alpha z to the power minus 1, this should not be equal to 0. Okay. Which makes h of z infinity. Now this should not be equal to 0 means it this term, the mod of magnitude of this term alpha z to the power minus 1, this should be less than or must be less than 1. So that if this is less than 1, then this term alpha z to the power minus 1 to the power infinity plus 1, if this is very less than 1, then this term will be very small. To the power n will be very small. Okay. To the power infinity plus 1 will be 0, approximately equal to the 0. Okay. Now, if we keep this value greater than 1, then this the power this term to the power infinity plus 1 will be equal to infinity. Okay, this will be infinity, then which makes h of z again infinity. Okay. Now, therefore, we only choose this alpha z to the power minus 1 equal to which is less than 1. Okay. Now, if this is equal to 1, if we make this is equal to 1, then this entire thing will be 0, which again will make this h of z infinity. Okay. So please understand there are three possibilities of this. So in denominator, we are having 1 minus alpha z to the power minus 1. So we can, this value can be greater than 1, less than 1, or equal to 1. So if you put this value equal to 1, then this denominator will be 0 and h of z will be infinity. Okay. So which we don't want. Okay. So we want convergence existence of z. Okay. Now if we put this value greater than 1, so then this term is also greater than 1 and to the power infinity, then which makes this whole term equal to infinity. So again, this term will be infinity. Therefore, this is also not feasible. The only feasible thing is alpha z to the power minus 1 should be less than 1, must be less than 1. Okay. Now, if this is less than 1, then this term mod of alpha z to the power minus 1 is less than 1. Okay. So, alpha by z is less than 1, then I can say this mod of alpha is less than mod of z. Okay. So if this alpha is less than this z, then the numerator is, this term will be 0 and this to the power 0 means this 1. So we will left with 1 divided by 1 minus alpha z to the power minus 1. Okay. If mod of z is greater than alpha, then this is the solution. If mod of z is less than or equal to alpha makes this is equal to 1. This term will make equal to 1. Therefore, mod of z less than equal to alpha, then we will get h of z equal to infinity. Okay. Okay. Now, the range where this h of z is not equal to infinity, that range or region is called as region of conversion, that is ROC. Okay. So h of z is not equal to infinity. The range where this is not equal to infinity, in this case, the region is where mod of z is greater than alpha value. Okay. Now this in the graph we can plot like this. So z plane, this is z plane. This is real z, this is imaginary z, j times I can say. Okay. And this is the circle of radius alpha. This r is equal to alpha. Now, if mod of z is greater than alpha value, in that case only h of z is exist, which is not equal to infinity. Therefore, the region is what? Outside this circle. So represent that region with the lines like this. Okay. So this is our region of convergence for the alpha to the power n u of n. Okay. So you also need to draw this region of conversion ROC for the particular sequence. Okay. So the outside this circle h of z will exist. Okay. Now, so we know that the z is a complex value with this polar form, that is r e to the power j omega. Okay, where omega is the angle. Theta or omega, you can use anything. Okay, now the region of the that is the range of this region of conversion is actually determined by the radius r value. Okay, in the Fourier transform, this r is equal to 1, but here it is not. We can choose this r value. So the range of this ROC is actually determined by the radius of the r value. Okay. Let us take another example. Okay. Now, this is the impulse response test. Now, in the starting lecture, lecture 1, 2, we have seen the LTI system. Okay. And we have seen the causality and the stability of the system. So the LTI system is evaluated basically on the its stability and the causality. Okay. And that is based on the H of n. H of n is the impulse response of the system. Okay. Now, based on this H of n, the causal system, we can say that if this H of n is equal to 0 for n less than 0. The causal system will be if the impulse response of the system. Okay. So impulse response of the system is defined as H of n. If this H of n is equal to 0 for n less than 0, in that case, the system will be causal system. Okay. Similarly, we can say the stability. Now, the mode of this H of n, magnitude of this impulse response, if we do summation of over limit minus infinity to infinity, and this magnitude value, if it is less than equal to some beta which is not equal to infinity, then the system will be stable. Okay. Now, the Z transform is another approach on evaluating the stability and the causality of the LTI system. Okay. Now we'll see one example for this. Or now, in case of Z transform, the causality, the system is causal. How to determine whether the system is causal or not? How to determine whether the system is stable or not? Okay. Now, in the Z transform, we are having the Z plane here. Okay, and this is the circle with radius r. Now, the causality of this LTI system will determine the shape of ROC. Okay, now here you can see ROC is outside the circle. Okay, now for the causal system, where the H of n equal to 0 for n less than 0, ROC is right-handed. Right-handed. Right-handed ROC means the outside circle. The region of conversion is outside circle. Okay. If you see the region of conversion is outside circle, then you can say that the given system is the causal system. Okay. So in using Z transform also, we can find out the causality of the system. Okay. Now, if we are having region of convergence inside the unit, inside the circle, we cannot say this is unit circle, inside the circle. Now for anti-causal system, so what are the anti-causal system? So in the anti-causal system, H of n equal to 0 for n greater than equal to 0. The causal system where n less than equal to 0, H of n is 0. In case of anti-causal system, n this h of n is equal to 0 for n greater than equal to 0. Okay. So in this anticausal system, ROC is left-handed. So left-handed ROC means ROC is in the inside circle. Okay. Now for non-causal system. Now non-causal systems means what? Where for n less than 0 and n greater than equal to 0, h of n is not equal to 0. Okay. So not equal to 0 means exists. It exists. H of n exists for n less than 0 and n greater than equal to 0. Okay. So the region of convergence is like ring shape. Okay. If you see the region of convergence for particular system like this ring shape or annular shape, this is also called as annular shape. So if this is if you see the region of convergence like this, then you can say that the particular system is non-causal system. Okay, one is the causal system, non-causal system, anti-causal system. Okay, so the causal system where h of n is 0 for n less than 0, non-anti-causal system where h of n is 0 for n greater than equal to 0, and non-causal system means h of n exists which is not equal to 0 for this limit. Okay, now in this example we have seen this example alpha to the power n u of n, and there we have also plotted this region of conversion. Now the region of convergence for this example is what? This is outside the circle. Okay, circle of radius alpha here. Okay, now from this ROC we can say that the system is causal or the signal is causal signal. Okay, this is a causal signal or this is having ROC right sided. Okay, so always when we solve the Z transform, this ROC, you also need to draw the Z plane, then this region of convergence, we have to highlight like this, you have to do. Okay. So this is the causal system, we'll see. Now, if we see this example, suppose we are having the signal sequence h of n equal to minus a to the power n or alpha to the power n u of minus n minus 1. Okay, so how we draw the u of n? U of n is basically having value 1 for the positive half. From 0 to this, we are having u of n. Okay, now u of minus n is what? U of minus n is, we can draw this, u of minus n is this is 0, u of minus n. For negative half, we are having values 1. Now in the example, this is u of minus n minus 1. Okay, so u of minus n minus 1, so it will start from minus 1. Okay, so u of minus n minus 1 is like this. So for minus 2, minus 3, minus 4, it is having value 1. Okay, great. This minus 1, beyond minus 1 on the left side. Now, this is anti-causal signal. What is the definition of anti-causal signal? H of n equal to 0 for n less n greater than equal to 0. Okay, so for this signal n greater than equal to 0, this h of n is 0. Therefore, this signal is basically the anti-causal signal. Okay, are you getting this? Yes, students?
So far, okay, doctor.
Okay. Now find the Z transform of this H of n. So H of n is what? H of Z, if I want to find out, this is summation from n equal to minus infinity to plus infinity H of n Z to the power minus n. Okay. What is our H of n? Our H of n is minus alpha to the power n u of minus n minus 1. Okay. Now we know that this u of minus 1 minus n minus 1, this only exists from the limit minus infinity to minus 1 only. Okay. Therefore, this summation is having limit. This is summation over n equal to minus infinity to minus 1. This is minus alpha to the power n z of minus n. Okay. Now, if we keep this minus sign outside summation, so minus summation from minus infinity to minus 1, alpha z to the power minus 1 to the power n. Okay, so again we can apply that formula, summation of a to the power n from limit, from lower limit n to m, like this. Okay, so if we apply this formula, so it is like this. Okay, now if we put the value here, this is the formula. Okay, so minus sign is outside this. Where it is. Okay, so this minus sign is there, so therefore this minus and this is plus. Again, for Z transform to exist for this h of n, this h of z should not equal to infinity. Okay, so which term makes this infinity? So this should not be equal to 1. Okay, now here, if this is less than 1, alpha z of minus 1, if it is less than 1, if it is greater than 1, what will happen? What will be the h of z? Okay, so if the magnitude of this alpha z to the power minus 1, if it is greater than 1, then in that case, this numerator first term to the power minus infinity will be 0. This to the power minus infinity means what? This means 1 by, this term means 1 by alpha z to the power minus 1 to the power infinity. Correct? If this is 1 greater than 1, so this whole term will be infinity. So 1 by infinity will be 0. Okay. So this term will make 0. And this is to the power 0 means this is 1. Okay. So you will get some finite value of h of z there. When this term is greater than 1. Now, if you choose this term less than 1, what will happen in that case? If it is less than 1, then this will be approximately 0 and 1 by 0 will be infinity. Okay. So in that case, this h of z will be infinity. That means it does not converge. Okay. Now, therefore, this will converge only for magnitude of alpha z to the power minus 1 greater than 1. Okay, so alpha mod of alpha greater than mod of z. So this is only converge for this. Okay, now we plot this in the z plane. So we are having z plane with real z, j times imaginary z. The value of radius r is basically equal to alpha. Now this is only exist when the z is less than this alpha. Okay, so the region of convergence is basically inside circle. Okay, so we are getting region of convergence inside circle. Therefore, if the region of convergence is inside the circle, then this system is anticausal system. Okay. So the previous example, that is alpha to the power n u of n, this was a causal signal. Now here this is anticausal signal. Okay. Now we'll see the next example. This example is about the non-causal system signal. Okay. Now the given h of n is 0.5 to the power n u of n plus 2 to the power n u of minus n minus 1. Okay. Now find h of z for this given h of n. So this is u of n, then this limit will, otherwise you can directly apply the formula here, that is summation over minus infinity to infinity. This is given h of n into z of minus n. Okay, now this split this term and again the summation limit. Now this is u of n, therefore the summation will go from 0 to infinity, 0.5 to the power n z of minus n plus, now this is u of minus n minus 1, we have seen in the previous example. What will be the limit for this u of minus n minus 1? That is summation will goes from minus infinity to minus 1. Therefore it is written like this, minus infinity to minus 1. Okay, minus infinity to minus 1 of 2 to the power n z of minus n. Okay, now solve this summation. So this we can write okay, so this we can write like this, 0.5 z to the power minus 1 to the power n. This term we can write 2 z to the power minus 1 to the power n. Okay, we can apply that formula. So this is equal to this to the power 0 minus this to the power infinity plus 1 divided by 1 minus this term. Okay, again we need to check for convergence of this. Okay, now for the first term here, this will converge when 0.5 z minus 1 is less than 1. Correct? If it is less than 1, then this term will goes to 0 and this is 1. So we will get some finite value of h of z. For the second term, this will converge when 2z to the power minus 1 is greater than 1. Why greater than 1? For greater than 1, it is this term will be 0 and this is 1. Okay. Now I will say 0.5 if this mod of z is greater than 0.5, then this will converge. Here 2 if this z is correct less than 2, in that case this will converge. Okay, so if this z is greater than 0.5 and this z is less than 2, in that region only h of z exists. Okay, therefore we will get this ring type structure. So the inside circle having radius zero point 0.5, the outside circle is having radius 2. Okay, so the region of convergence is this between these two circles. So z is having limit from minus that is zero point 0.5 to 2. Okay, so if we are getting this ring type structure, in that case the system is non-causal. Okay, the system will be non-causal for this. Okay, now let us take another example. Suppose this sequence is given h of n equal to 1 1 1 1. Arrows here means n equal to 0. Okay, now find out whether the system is causal or not, whether the system is causal, anti-causal or non-causal. Okay, now apply the z transform here. So z transform is h of z, limit goes from minus infinity to infinity, h of n, z of minus n. But the given sequence is from 0 to 3. This is 1, 2, 3. So therefore summation from 0 to 3 here. Okay. So h of n is having value 1. Therefore this is equal to 1, z of minus 1. Okay. Now if we do the summation here, so this is z to the power minus 0, that is 0, which is 1. 1 plus z minus 1 plus z minus 2 plus z minus 3. So if we put this z minus 3 common, so this is z3, z to the power 3 plus z to the power 2 plus z to the power 1 plus 1. And this is written like this. Okay. Now how to find the region of convergence for this? Okay, so to converge z, so z can takes any value except z equal to 0, because in the denominator we are having z to the power 3. If z equal to 0, in that case this h of z will be infinity. Correct? So for the convergence we don't want this. So the region of convergence is basically except z equal to 0. So the ROC is basically the right sided here. Okay. So the ROC is basically the entire Z plane except Z equal to 0 here. Okay. And therefore we can say that this is the right sided ROC, and therefore the system is causal. Okay. So the system is causal here. Now can you find out for this h of n? Now this is the given h of n. Can you tell me whether the system is causal, anti-causal or non-causal? Yes, students. Now arrow is at the last value. So this is n equal to 0. So this is minus 1, minus 2, minus 3, minus 4. So summation is from n equal to minus 4 to 0. Okay. Can you find out whether the system is causal, anti-causal, non-causal? Yes. Find h of z for this. What will be the h of z? Yes, what will be the h of z for this? So for n equal to 0, it does not exist having 0 value. So we can take our summation from -4 to -1, correct? Which is having 1 value. So z of -1. So this is written as z to the power 4 plus z to the power 3, z to the power 2 plus z to the power 1. Okay. Now, this h of z will be infinity when z equal to infinity. Correct. So the region of conversion will be entire z plane except the value z equal to infinity. Okay. So in this case, the ROC is basically the left sided. Okay. So this ROC is left sided where this magnitude of z is less than infinity. Okay. So this is the entire z plane except z equal to infinity. Therefore, this system is, or this signal sequence is left sided means anti-causal. Correct? Have you understood these two examples? Yes, students? Is it okay with
Doctor,
you?
may I ask one question?
Yeah, yeah.
Why did we just ignore the zero?
Why this zero?
Yeah, why did we just ignore the zero?
Because if you do summation, this is again summation from an equal to 0 -4. I will solve this just a second. So if I want to find the z transform for this, so h of z is summation from n equal to -4 to 0, correct? H of n, z to the power minus n. Okay. Now in the sequence from -1, -2, -3, -4. So summation from n equal to -4 to -1. H of n is 1. So 1 into z to the power minus n. And plus, we left with only what, n equal to 0. So summation is not needed. So n equal to, at n equal to 0, the value of h of n is 0. 0 into z to the power minus n. Okay, therefore, this whole term is 0. Is it clear now?
Yeah, Doctor, thank you.
So 0 into this term is 0. So we have ignored this part. And we have directly written here. Okay, so this value is very important. In the previous case, all are 1 here. Are you getting this? If it is 0 here, then we will skip that term or that term will be 0. Okay. Now, can you find out the Z transform for this example? Now, the given sequence is what? Arrow is here means n equal to 0. This is 1, 2. This is -1, -2, -3. So summation will go from n equal to -3 to 2. Correct? And all are 1. Therefore, we will keep this summation only. Okay. Now this is written like -3 to 1 and n equal to 0 to 2. So if you separate this summation, so what if you solve this, this is z to the power 3 plus z to the power 2 plus z to the power 1. For this summation, it is z to the power minus 1 plus z to the power minus 1. I will write this. Z to the power 0 plus z to the power minus 1 plus z to the power minus 2. And if we keep z to the power minus 2 outside, this is z to the power 2 plus z to the power 1 plus 1. And this minus 2 again we can write in denominator. So we will get this. Okay. Now, how to find the region of convergence for this? H of z is this. Okay. Now, for this, if we keep z equal to infinity, then this will be infinity. If we keep z equal to 0 here, so this term will be infinity. So the region of convergence is basically except z equal to 0 and z equal to infinity. Entire z plane, but except these two values, z equal to 0 and infinity. Okay. So this, we can say that this is having the ring structure. Okay. So z is inside 0 and infinity. So ring shape ROC we will get here. Okay. So the if when we draw the ROC region of convergence in Z plane, so here you cannot draw a circle because the higher limit is infinity. So you need to show like this only, the entire Z plane, but you need to write there except Z equal to 0 and Z equal to infinity. So we will get the ring structure, ring shape ROC. Therefore, the system is non-causal. The signal is non-causal. Okay. So we can say that the signal is non-causal here. Okay. So you can practice these examples at home, or we will solve some example tomorrow maybe. Okay. So for today, we will stop here. Tomorrow we will see the stability, how to find stability from the using the Z transform. Okay. So this we will do tomorrow, stability part in the tutorial. Okay. So for today, we will stop here. Please practice these examples at home. I will share this PPT. Yes, is there any doubt?
No, doctor.